Okay, so we're going to use a new stepper motor this time. It's a 1 week project. If you look at the schedule, I think this one, I haven't put a deadline here yet, but it's due next Thursday. But I'm confident you guys can get it done before that. It's a cheaper stepper motor and very easy to use. And you can build a robot arm out of it easily. I used to have a longer tutorial, have a 2-joint robot arm. It takes too much time. You have to use like 1, 2, 3, 4 stepper motors and 4 drivers with them. It's not a really super fun project, but it takes a long time. So I just removed it. So I just took the first step out here for a 1 week project. So we can move to the balancing robot later. And you can see, make the connections from the driver to the stepper motor is not that difficult. Especially, it's just a little connector. You just plug into it. It's from the Arduino kit, actually. So here's the driver, that's the motor. And there's a little tutorial, but you don't have to watch it. If you want, you can. But looking at the example code, you can see there are 2 or 3 functions you are going to use. I think the first one is mass stepper. All right. You have to specify the steps per revolution. It's similar to the NEMA 17 that we just used. So this one has 38 steps per revolution. And I think these are digital pins from the Arduino to be connected to your stepper motor. And so mass stepper dot set speed 5. If you watch the video, you can tell usually we don't use anything higher than 19 RPM. So the unit for this number is RPM. So make it lower than 19. Otherwise, it's drawing too much current, make it overheated. So it's very slow. That's why I'm not using this one for the balancing robot. It's going to be a super slow robot, snail robot or something. And so this one, my stepper dot step. So you are specifying how many steps you want the stepper motor to spin, right? So for 2038 steps, it's for 360 degrees. So you can calculate how many how many degrees per step. And if you want the stepper motor to rotate like 90 degrees, you can calculate how many steps you need to rotate the stepper motor for 90 degrees. And if you put a negative sign in front of it, it's rotating counterclockwise by that many steps. Okay, and you can convert into degrees. Pretty simple. Okay, the direction. Negative size is counterclockwise.
Oh,
yeah, direction. The positive is clockwise.
Oh, I didn't see.
So you have directions. You have degrees per step, right? And it's pretty much everything to rotate the motor. Very simple. And it's super precise. The reason we want to use a stepper motor instead of DC motor is it's precise, right? If I'm rotating like 45 degrees, it's going to be 45 degrees. But DC motor, you turn it on, it's plus minus 10 degrees. So that's why we're not using a, yes, you can find a lot of examples by using DC motors to balance a 2-wheel robot. It's very difficult. So in the future, if we're selling our product, we are either using a encoder controlled DC motor or a stepper motor, the NEMA 17, the one we have been using. That one is $8 for each, I think. Yeah, we just have to make sure we have good performance of the robot. So that's the first one I want to use. A second one, you probably have seen some of the robot arms are being controlled by an encoder. So you have a little knob here. You want to move the robot arm for how many degrees, you just control it over here, right, on the control unit. So that control unit can be realized by using the encoder. So I think this is a very important tool that you guys need to know how to use it. So for the encoders, it works like a spinning plate with two sensors. A lot of encoders are using optical sensor in it. I'm not really sure if this one is optical sensor based. So what's happening is if the two sensors, since I don't have the schematic of it, so but the thing is, if the two dots, for example, the two dots are like optical emitters, and these are plates are going to block that emitter's light, and if the plate is, for example, you are rotating it, okay, and the plate is going to move towards these two emitters, and whenever the little emitter is on the top of the, or being blocked by the plate, it's going to output a rising edge. Okay. I don't know the schematic of it, so I don't know like what's really going on inside. But what's happening is, if you only care about the electrical signal, what's happening is when you spin it, okay, where imagine these two emitters are not moving, for example, okay, if you move the plate, and whenever the plate is on top of it, it blocks the signal and giving a rising edge of the circuit. It's very easy to design that circuit to implement this mechanism, but we just don't know what's really happening. But it can happen, right, easily. We just need to know that when we spin it clockwise, which emitter will be blocked by the plate first. Yeah, if you rotate it counterclockwise, B will be blocked first, right? So we can write a program, okay? For example, the top one is A, okay, and the bottom is B. If it's giving you a sequence like this, where the plate is being rotated right now? Clockwise, because A is giving a rising edge first. Okay, so the algorithm running behind the scene is when A changes, because you know in the debug script we have written that we keep reading A from the digital pin, and we assign a state to A, and we give a last state of A as well, right? So by the end of the script, we are checking if we are sending the current state to A again, to a current A, but we are comparing if the state of A has been changed. So on the very top, we assign the current state of A to last state of A from the digital rating. And at the end, we assign the current rating to the current state of A, right? And the if statement, we are comparing if the last state A has been updated. Then we get into the if statement, get into the loop. So for here, same principle, okay? What can we do to verify the direction of the rotation? But how do we, but in C, right? In C, how do you manage it if which one's first? That's maybe doable, but you have to keep the timer on all the time. It consumes a lot of power, and but how to do the sequence? Which one happens first?
We just loop through, and if one gets updated in that, like I'm assuming our clock speed is faster than it. So if you just set a flag, it'll update the flag with whichever one changed, and then the next one will change after that.
Mm-hmm.
So we don't really care about the second one, just the first one.
Mm-hmm. So what if So you are detecting which one changes. Yeah, that might work. If you look at the algorithm over here, the way to detect that change is whenever you're just looking at A to make it easier, right? Just looking at the state of A. When A changes, right before A changes, if both A and B are in the same state or different state. Just look at it.
Oh, right now.
They're in the same state. But when A changes, right before A changes, both A and B are in the same state. Then it rotates which direction?
But we don't know what direction.
It doesn't matter. I mean, when right before A changes the state. So for example, you can imagine both A and B's can be in this gap, or they are both being blocked by the plate, right? That's the two possibilities. But when A changes the state, it could be from the gap move to the underneath of the plate, or from here to here, right? So that's the two possibilities of the A when A changes. That makes sense? Did you see the two possibilities when A changes? It could be from, if you, for example, if we rotate it clockwise, right? Rotate clockwise. So when A changes, it could be A from here to here, or A probably was here at A from here to here. So A changes. We can detect the change because it's rising edge. So we can detect the change, no problem with the C when we program it. But right before A changes, if A and B are in the same state,
But once it rotates the first time around, they're not going to be in the same state no matter what.
what do you mean? No, I mean right before A changes.
But when the timing of the wait,
So we are assuming the width of this plate is exactly the same. Can only fit two of the emitters in there, right? So when A changes, if right before A changes, if A and B are in the same state, it's rotating clockwise. Is that correct? Okay. For example, right now in this current state, right, A and B are in the gap. So when you rotate it clockwise, A will get into will be blocked by the plate first. So A changes. So right before that, both A and B are in the same state. Same situation if you move both A and B enter the plate, and then you rotate it. So A will be moved outside of the plate, but right before that, A and B are both blocked by the plate. So right before A changes, both A and B are in the same state. Then it rotates clockwise. But imagine that if it's being rotated counterclockwise, okay, so the plates are moving counterclockwise. So when A changes, A and B are in a different state. For example, it moves, so the plate moves to the halfway here, right? And the next millisecond or something, and A is going to change the state, but B is already blocked by the plate. So when A changes, both so A and B are in a different state. Okay, so in that case, it's rotating counterclockwise. Think about it for one more second. You're getting it. You're getting it? You?
Would it just be easier to detect whether it's turned on or not, and if it's turned on first before the next one?
Because B can be either on or off, right?
Right, but you also have on and off on if it's high or low, and if it.
So both B and A can be on and off when the other one changes. So it's going to be a lot of situations to put into the if statement, right? There must be a different way to do it, but this is whatever was designed by the, I think it's one of the standard way to do it for the encoders. All right. It's really sweet because when you rotate it, you can feel there are a few stops, how to say that, you can feel the clicks. So it's not a continuous device, a knob. I don't know how many or steps. I don't know how many steps per revolution, but it doesn't matter because it's always the same, sending out the same signal. So the only outputs are going to be the pulses. Okay, so it doesn't have a degree count in there. Doesn't have a stop. So it's just keep outputting all the pulses in a different sequence. And the connections to the motor and to the Arduino is very straightforward. Okay, you make the connections and repeat whatever I did in the video, right? It's a very reasonable 1 week project. I didn't provide the code for this demonstration, but I provided the fundamental encoder, script to display something over here, and also the code for the stepper motor as well, which is the one over here. So you can directly copy and paste. But the last one is not provided, but I think should be very simple because when you output a signal, you detect a change. It could be clockwise or counterclockwise. It's basically you are synchronizing the movement of the encoder with the robot arm, but it's just a one joint robot arm, very simple motor, right? So rotate once here, the motor will rotate once. Okay, this is this week's task. And also, if you guys have some spare time, you can start thinking about this robot design, because what I'm trying to do this time is using, I mean, probably are going to use the card like you guys used over here. I mean, for the final product, not for the one you guys will do at the very beginning. So because you want to demonstrate your code or test your code on the commercial balancing robot in the lab, right? Test it, see if that works. And then I want to move it to a car frame similar to the one we used over here because it's cheap. Want to use this one?
That's lightweight too. I don't think it might still present rotate slowly. Yeah. Well, I'm thinking on the fails.
Well, yeah, when I was doing it 2 years ago, though, I would like duct tape weights to the top of it so it would fall.
Because you used a wrong not a wrong code actually. That was my code. Sometimes it's not optimized for all the situations.
Yeah, it's been so long trying to get that PID.
Yeah. But this time I think there will be a lot of fun because first we have the code already tested by other people, and we simplify the code instead of using the one posted by the original author like the one you used. I think we are using a totally different way to organize the PID controller. Although I think we should do something like it could be an encoder, could be, I don't want to use a screw or the potentiometer. It could be something else that we can tune that PID parameters in real time instead of tune it and then program it. You know what I mean? So if you have a balancing robot is trying to balance itself over there, and it can visually tell the P gain is too much, then we just tune it directly using the knob instead of. So you have 3 knobs, right? You tune this manually in real time and visualize the stability of the robot. That would be really fun.
The DAC or the ADC. So you only have 10 to 24.
It has 3 channels. More than 3 channels. You have A0 to A5, right?
Then you just use multiple.
You can just use multiple ADCs, right?
Yeah.
It's just reading from A0, analog read from A0 or A5. If you use a potentiometer, definitely. So I think we have the knob potentiometer. Remember the one? Yeah, with the knob on the top, right?
Yeah.
Instead of I don't want to use a screwdriver. It's difficult to put it there. So the knob is better. So we use a PID. So usually you start with P first and then INDs. We'll cover that later if you haven't done that. And I think that can be a really good educational kit. The reason why I don't use this one is because it's cheap. but I don't want to use a DC motor here since I was looking at one example, the commercial product developed by another one was trying to raise some funding for that project. And he used this DC motor, and he even delivered products to customers and didn't work out really nicely. Mm-hmm. So he was able to tune his robot, but the ones being assembled by the customer use the same code and it doesn't work at all because the motor doesn't perform consistently. So we may have to use a encoder-based stepper DC motor or use a stepper motor. So what I'm trying to do is using the ESP. I don't know if we can do it. That's enough number of pins for the ESP32 cam. So if the ESP32 cam can directly do a motor control by putting the robot car flat, right? So it's actually crawling, probably, So that's one of the way to drive the car. But if you hold it up straight, upright position, and it should trigger that two-wheel balancing mechanism or mode. So what we need to do is we have to cut the plastic here from, because when it stands on the table, we have to cut the tail here, right? So that the wheels can, it's not being blocked by the tail here. So I have to cut from here. And where? Here?
You don't want a camera on a robot that's constantly like shaking back and forth. It's like
no, it's not that actually shaking back and forth. It's very stable if you can do it well.
Oh, really?
Especially using the NEMA 17 stepper motor. It's really stable actually. It's very very doable. I can see some of the the balancing robot are in some of the office buildings. They are delivering like sandwiches. It's actually I also can even climbing onto the stairs. But it's very complicated ones.
They like cruise down New York Street.
Yeah, it works really well if you can do it, manage the PID controller in the proper way. So it's just a thought. We don't have to, but I think it's making this product really unique. You can find a lot of this balancing robot being sold for like $80 on Amazon. If you are making another one, so what's the difference?
Make like a transformer, so it's a car, and then you like fold it apart or something and put it back together, and then it's on
That's
two
right.
wheels vertical.
We just need to 3D print
A motor that does it. You hit a button.
robot. That's exactly what this one is doing, right? If you put it down, it's a car. If you hold it upright, it's a balancing robot.
We can put another motor in to transform it from the car to the two-wheel.
Oh, transform it into a.
Yeah. Now that would sell.
And have a little speaker on it to digitize the sound, right?
Talk or something. We could give it the Google API, and it can listen to you and respond back. It can be like an Alexa too.
Mm-hmm.
Hello, master. You wake up and it's like crawled up onto your bed.
You just have to make sure it doesn't have cellular. That way it's just confined to a home.
Yeah, you're right. You're
outside.
Right. Short battery life.
Right.
We don't have to use their frame. I'm thinking if you are using that big stepper motor, we may need a bigger wheel eventually, right?
Yep.
Yeah, we still have a week to think about it, so never mind. So this week, let's just focus on that. So this motor is mainly used as an actuator instead of a driving motor for the car or vehicle. It's super slow. But the advantage of using that is so cheap. I think it's under $1 instead of the other one, which is like over $8 or $9 for each.
So if we put a current through it, it should go faster.
I don't think so.
So if we put a massive inductor up the circuit,
stepped up to like 20 amps.
It's probably just gonna blow it up. I think it has its limits. I think because I was trying to search for any of the robot cars are using this one to drive them, but I didn't see even one example of using this motor to drive a car running at a reasonable speed. Most of them are just robot arms moving the joints and use it as an actuator. Right. I think the main goal of this tutorial is to let you guys practice with the script using the encoder and the stepper motor. Okay, that's it. Because encoder is important. It's being used a lot in many cases. Yep. Okay. Let's go to the lab, and I'm going to give you the